In this video, I'm going to dive into buffers. We need to know some information about buffers, and then we'll do some problems here with buffers. So we already know that buffers are solutions of anytime you have a weak acid and its conjugate, or a weak base in the presence of its conjugate, and these buffers resist changes to pH. All right. A buffer is literally going to try to resist any of these changes in pH and try to keep a pretty stable pH. So anytime you have a weak and its conjugate, that's a buffer. So as acid would be added to this solution, if you have a buffer that's made of a weak and its conjugate, if acid is added to it, the base part of the buffer would attack the acid and neutralize it and prevent the pH from changing. And then vice versa. If you added a base to this buffer solution, the acid part of the buffer would attack the added base, destroy it, and prevent the pH from going up. So that's how these buffers actually resist changes in pH, because they have an acid part and a base part, and they just attack the opposite part that's added and they destroy it. All right, and they pretty much resist these changes in pH to a certain point. Basically, the weak acid or base and its conjugate cannot consume each other. If you have a weak acid and its conjugate present, they don't react with each other. If you have a weak base and its conjugate present, they don't react with each other. All right, so this is why these buffers work. The pH will remain stable even if you dilute the solution with water or water is lost through evaporation. That pH is going to remain stable. So just be careful with that, right? That pH is not going to change even if you add water to the buffer or if you make water evaporate here. So just so you understand, a buffer is going to be when you have a weak acid being combined with its conjugate base. You mix them together, they don't attack each other. So then there's an acid component to that buffer and a base component to that buffer, which could destroy acid or base that's added and prevent those changes in pH. There are two ways to make a buffer. And the first way is the most obvious way because it's the definition of a buffer. If you have a weak acid and its conjugate, that will form a buffer. If you have a weak base and its conjugate, that will form a buffer as well. So basically, you would just have to, for example, here, take acetic acid and mix it with a salt that contains its conjugate. So sodium acetate here. Realize that if this is the weak acid, all right, you need the conjugate of that acid to be in the salt. So you have to realize here, when I remove the H plus, the conjugate of that weak acid is C2H3O2 minus. So the salt needs to have the C2H3O2 minus in it, then that makes the conjugate present there. So you have a weak acid and a salt of its conjugate. That's going to form a buffer when you mix them together. It's the definition of a buffer. Same thing here. NH3 is a weak base. So being able to identify these strong acids and strong bases is important here again. So you can identify the weak ones that exist here. So this is a weak base, NH3, is going to be added here to a salt of its conjugate. You would need to say, okay, when I add H plus to this, because this is a weak base, when I add H plus to this, NH4 plus is the conjugate. So the NH4 plus would be in the NH4Cl here. So you need to look for the conjugate in the salt. As long as you have a weak acid or base and its conjugate present, that's going to form a buffer. So this is the easiest one to identify because it basically goes right along with the definition of a buffer. The second way to make a buffer requires a little bit more thought. When you first look at this, it doesn't seem like you would have a buffer, but then when you consider the reactions that take place and what's remaining, you do get a buffer forming. All right, so you could add some strong acid or base to a weak base or acid in order to make the conjugate salt. So if we look at an example of this, say if we added some NaOH here to the weak acid acetic acid here. So we're adding some strong base to a weak acid. Well, if you remember back to our titration problems, as long as you don't add enough to reach the equivalence point, you would be in that buffer region. And that's exactly what you're looking at here. you have a strong base being added to a weak acid, but not enough to go past the equivalence point, so you have a buffer. Basically, the conjugate salt that forms here, the C2H3O2 minus, would be forming, and there would still be some of that there along with the weak acid. So basically, you would have some of this weak acid still remaining and its conjugate present. That's the definition of a buffer. Notice the key word here, you're adding some NaOH. If you added, past the equivalence point, you would no longer be in that buffer region. Typically, if you're given this, on a, multiple choice or something, they're not going to specify amount. You would just need to realize here that there is a place where you could add a strong base or acid to a weak acid or base and get a buffer forming. So this one requires a little bit more thought. It's not the definition of a buffer, but because of the reaction that takes place and what forms with the weak that was present, you get a buffer forming. So you really need to think about this. Or there's another way here. You can take some strong acid or strong base, adding it to a salt to make the conjugate. Again, you're only adding some here, but an example of this would be, what if you add HCl to NaF? On first glance, this is a strong acid. This is a salt. You might say, well, that's not a buffer. That doesn't fall under the definition of a buffer. But if you look at the reaction that takes place, if you actually write this out, one of your products here is HF. That is a weak acid. So if you have a weak acid present now and you haven't added enough to destroy all of the NaF, you would still have F minus ions floating around. Well, the conjugate of HF is F minus. That would be a buffer. You have a weak acid present with its conjugate, you have a buffer forming. So this way that we're looking at here, these two ways, they require a little bit more thought. So if you're given a question where you have to figure out, does this set of, do these two substances make a buffer? You got to look first, do I have a weak acid and its conjugate or a weak base and its conjugate? Because that's the definition of a buffer. Or can I form a weak with its conjugate here by mixing these two things, and then I do have a buffer? That requires a little bit more thought. But these are the ways that you can make a buffer, and you need to be able to look at, two substances and see if they will form a buffer or not. I want you to look at this example here. It says, which of the following could be added to a solution of sodium acetate to produce a buffer? And you have to choose any here that work. So sodium acetate here is your solution. Which of these four substances could you add to sodium acetate and produce a buffer? There could be more than one. There doesn't have to be. But what I want you to do right now, pause the video, think about the reactions that would happen here, and if you get a buffer for any of these. So pause the video and try this right now. Hopefully you realized here the first two would be able to produce a buffer and the last two would not. So the first one, the acetic acid, well, that's just the definition of a buffer, all right? Acetic acid is a weak acid. Its conjugate here would be the acetate, all right, which is in sodium acetate. So that's the definition of a buffer. Weak acid in the presence of its conjugate, that forms a buffer. But for the next one, the hydrochloric acid, it would also form a buffer, but you need to look at the reaction here. All right. At first glance, you might say, well, that's a strong acid, so that's not going to be a buffer. But if you just mix some of these together here, if you look at the reaction that forms, you actually get a weak acid forming here. And if, as long as you don't, go past the point of destroying all of the sodium acetate, you would have its conjugate, the C2H3O2 minus, still present. So you formed the weak, and it would be in the presence of its conjugate. That's the definition of a buffer here. But the last two are both salts, and if you do the double replacement reaction, you'll quickly realize you get like the same substances, the same salt. You don't get a weak and its conjugate. So anytime you need to do this, consider which substances might form if these things are going to react, and then see if you have a weak and its conjugate present. And then you'll know that a buffer would form. So sometimes you might actually need to write a reaction here if you're not sure in order to confirm that a buffer would be able to form here. Buffers are actually an example of the common ion effect. You could do buffer problems using kind of the common ion ideas, but it's easier just to use the Henderson-Hasselbalch equation. Buffers are most effective, or what we call ideal, when you have equal amounts of your weak and the conjugate, right? So an ideal buffer would be when you have equal amounts or equal concentrations here of the weak and its conjugates. That's something important. If you're ever asked anything about an ideal buffer, or you need to use an ideal buffer here, you just need to have equal concentrations of the weak and its conjugate. And remember here, these buffers are going to resist changes in pH until the conjugate acid or base here is pretty much used up. All right, so this pH will constantly be resisting as much as it can, and then when you use up one of the parts of the buffer, then it's going to not be able to resist those changes in pH anymore, and you'll see the pH start to change. Essentially, the buffer won't work anymore. You definitely need to be able to understand buffers here kind of on a molecular level, or looking at this in terms of the ions. Realize here that if you had a buffer, you would have a weak acid and its conjugate. So if we're looking at this buffer right here, you can see this HAN. It's just saying hydrogen is attached to some anion. Well, that would be a weak acid, right? The conjugate of that would be when you lose the H plus, you just have the anion with the minus charge. So in this beaker right here, we have a buffer because we have a weak present with its conjugate. So what this is trying to show you is how this can resist changes here in pH. If I added H plus to this beaker, if I try to add acid to this beaker, what's going to happen here is that conjugate base is going to attack and neutralize that acid that I'm adding. As the H plus is added, this conjugate base will neutralize that. And you'll see here, that means you're forming in this beaker here, after you add the acid, you're forming more of the weak. But it would still be buffering because there's still more of that conjugate base here present that could react or attack with any acid you're adding. And then the opposite is true here. If you have your buffer and you add OH minus from your strong base, what's going to happen here is any OH minus you add is going to be neutralized by that weak acid. The weak acid that's present in the buffer will attack the OH minus, destroy it. You'll form water and obviously more of the conjugate. Right? So you need to realize here, whether you add acid or base to a buffer, there's a part of the buffer that can attack and destroy either. All right, that's very important. That's how a buffer resists changes in pH. Whether you add acid or whether you add base, the pH is not going to change because there's something in that buffer to react and destroy each. Definitely understand what's happening here as you add acid or as you add base. Understand which part of the buffer would be reacting with it, and maybe the reactions that would be taking place to neutralize the added acid or base. Again, this picture is just trying to get you to see here what's happening when you add acid or base to a buffer. So our buffer has the weak acid HF in it, along with its conjugate F minus here. So a weak present with its conjugate is a buffer. And notice we said it's ideal when you have equal amounts of each. So if you go and try to add acid to this buffer, what's going to happen is the conjugate is going to react with that added acid. So notice here, the amount of the conjugate goes down, but it's going to form the weak. All right, so the weak goes up. But notice the pH would not change because the added H plus was destroyed. And then when you have this buffer, if you were to add OH minus to it, the weak acid here, the HF, is going to attack and react with that to destroy it. So the amount of HF goes down in your buffer, but then the amount of the conjugate goes up. But again, notice the OH minus was destroyed. So the pH is not going to change here. All right, and this buffer would continue working until one of the components got destroyed. And definitely you need to understand this in terms of the molecules themselves, as well as we kind of just went over on the previous slide. Definitely need to understand how a buffer is working here to react with acid, to react with base, in order to keep the pH stable. We're going to work on finding the pH of buffers here. And again, these are not new problems. You could technically use common ion effect from equilibrium, or you can use Henderson-Hasselbalch like we saw in titration problems for the weak strong, for the one region there. We know that anytime we're doing one of these weak acid strong base titrations or weak base strong acid titrations, you're going to have this buffer region from the time you add your first drop of titrant up to the equivalence point. All right, you're going to have a buffer present. You're going to have a weak present with its conjugate, so it's a buffer zone, and you have to do this Henderson-Hasselbalch as we've seen. So if we're looking at our titration curves, so from the minute you start adding titrant up to the equivalence point, you have a buffer there, and obviously here on the other curve, we're adding strong base to a weak here, weak acid. That point from when you add your first drop up to the equivalence point is going to be the buffer region. So anytime you have a titration here of a weak with a strong, you know you're going to have that buffer region right after initial up to the equivalence point. But we've already seen problems like this, and we've already used the Henderson-Hasselbalch equation for those problems. But now we're going to do some more buffer problems using that equation. Here's the Henderson-Hasselbalch equation again. Remember, on your equation sheet, you're only given this version. Remember, the pH version has pKa in it, and your concentration of the acid is on the bottom. But when you're doing the pOH version, you need a pKb, and the concentration of your base is on the bottom here. All right, so you might need to use either of these. You got to pay attention to which one is your weak, essentially. If you have a weak acid, you need to use your pH version. If you have a weak base, you need to use the pOH version. So always let the weak tell you which version of the equation you need to be using here. Just kind of like a little FYI, this equation technically becomes a little less accurate as the acid or base becomes stronger or the concentrations become smaller. So in theory, this could affect your lab data a little bit. It's not a big deal for us. I just wanted to make you aware in case we maybe see any kind of differences here in lab that technically it does become a little less accurate under certain conditions. But definitely we're going to need to know how to use this equation and do buffer problems with this equation. Let's look at a pretty simple example here to start. We want to know the pH of a buffer of a 0.12 molar HC3H5O3 and a 0.10 molar NaC3H5O3, and they're giving me the Ka value. The first thing you need to realize, they did tell you it was a buffer here, but realize this is obviously not a strong acid, so it's a weak acid, and you can see here the conjugate of that, when you remove the H plus, would be C3H5O3 minus, and that is here in the salt. All right, so the C3H5O3 minus is here. So we have a weak present with its conjugate. This is a buffer. So if we are going to do the Henderson-Hasselbalch equation, because we have a weak acid, we need to use the pH version of the equation. In order to do this, though, I'm going to need a pKa. So I have to find that first. I know pKa is equal to the negative log of Ka. So in the problem, they gave me Ka. So I know I'm going to have here the negative log of this 1.4 times 10 to the minus fourth. And when I do that, I get 3.85. So that's my pKa here. So I need to plug into my equation. You need to write your equation. So we have pH equal to pKa plus the log concentration of your base all over the concentration of your acid here. So now when I'm ready to plug in, I'm solving for the pH here. So I'm going to have pH equal to 3.85, that was my pKa, plus log here, concentration of the base. Well, in this case, that's the conjugate. So that's the salt part here. That's going to be 0.10 all over the concentration of the acid, which we said was 0.12. When you do the math here, again, I would make sure you can do the math and get this answer. It comes out to be 3.77. So this would be the pH of this buffer if you had these values. So that's a pretty basic buffer problem, realizing that the acid was weak. So I needed to use the pH version of the Henderson-Hasselbalch, and I needed the pKa. Remember, acid, concentration of the acid would go on the bottom here because it's the pH version of the problem. But the pH comes out to be about 3.77. I want to talk a little bit here about buffer capacity. This is referring to the amount of acid or base the buffer can neutralize before the pH of the buffer begins to change. Remember, the buffer is going to resist changes in pH here. So there's a certain capacity that exists. There's a certain amount of acid or base that can be added to a buffer that it can destroy before it stops buffering. So obviously, this is going to depend on the amount here of the acid or the base in the buffer itself. If you increase the amount of acid or base in the buffer, the more resistant the buffer is going to be to changes in pH. So if you have higher concentrations here of your weak and the conjugate, the buffer is going to be more resistant to those changes. It's going to be able to last longer. Buffers typically act best here when you have the pH equal to the pKa of the weak acid, if it's a weak acid in your buffer, or when the pH equals the pKb, if it's a weak base. All right, because that's where the two concentrations here are going to be equal. Remember these ideal buffers? Ideal buffers when you have concentrations of the weak and its conjugate being the same. So if you need to actually look at this in terms of the Henderson-Hasselbalch equation, remember pH equals pKa plus log of the concentration here of the base over concentration of the acid. So if you have these concentrations of the weak acid and its conjugate being the same, all right, notice here that would be the log of 1, which essentially cancels this out, and you have the pH equal to the pKa. So the reason why buffers act best where the pH equals the pKa is because that's where these two concentrations are equal. That's when you have an ideal buffer. So this ties in beautifully with that idea of an ideal buffer having those equal concentrations. When they're equal, this basically cancels out. The log of 1 is 0, and this gives us the pH being equal to the pKa. So if you have a buffer, all right, having a pH equal to the pKa, that's when this is going to be acting the best here. All right, so this idea of buffer capacity, the buffer being able to neutralize a certain amount of acid or base is important here. If you increase those concentrations, obviously the buffer can be more resistant to these changes in pH. Anytime you have a buffer here with that 1-to-1 ratio of the conjugate to the weak, that's going to have the greatest buffering capacity. All right, that makes sense. That's an ideal buffer. You have equal amounts of the weak and its conjugate, so there's equal amounts there ready to react with any added acid or base here. Essentially, the maximum amount of acid that could be added to a buffer would be equal to the amount of conjugate that you have present in your buffer. And then vice versa, the amount of, base that could be added to a buffer depends on the amount here of the acid part of your buffer that you have in it. Okay, remember, if you're adding acid, it's the opposite part in the buffer that's going to react with it to destroy with it. So if you have larger amounts of these components, if you have more of the weak and its conjugate, it makes sense that the buffer is going to be able to resist changes to pH here more. And ideally, you would want this to be a 1-to-1 ratio because that's giving you a large amount of each present to be able to react with any acid or base that's added. You may see questions here about, is a buffer still a buffer? Well, there's two ways that a buffer kind of is still working or a buffer is still buffering, if you will. If you have a pH within plus or minus here, within the pKa plus or minus 1. So if you know the pKa and your pH is within plus or minus 1 of that, it's still buffering. Another easy way to look at this is if you look at that ratio in the Henderson-Hasselbalch equation, the concentration of your conjugate to the weak. If you actually just divide those two numbers and they fall within this range of 0.1 to 10, then it's still buffering. So basically what that means here, if we look at the Henderson-Hasselbalch equation, we know it's pH, pKa, all right, plus the log concentration here of base all over the concentration of the weak acid. So if a question says, is this buffer still a buffer? All you do is take your concentration of your conjugate divided by the concentration of your weak acid, right? Just this part of the equation, essentially, the concentration of one divided by the concentration of the other. If you get a number that's between 0.1 and 10, then you know that it's still buffering and the buffer is still working. All right, so that's just something you need to watch out for. If a question asks that, just quickly divide those two concentrations and see if the answer you get falls in that range, and then you'll know that the buffer is still working. Let's look at an example here. This says how many moles of NH4Cl must be added to 2 liters of 0.10 molar NH3, they're giving me the Kb of that, to form a buffer whose pH is 9.00. And we're assuming that the addition of solid does not change the volume of the solution. So the first thing you need to realize is here, we're asked to find the number of moles of a salt. And we're going to have to get this value using the Henderson-Hasselbalch equation. We're not asked to just find the pH of the buffer. They gave us the pH of the buffer. All right. First thing you need to realize is, remember, the weak component of your buffer determines which version of the equation you're using. Well, in this case, the weak is the NH3. That's a weak base. And you would know this because, look, they gave you a Kb. So the weak part of the buffer is NH3. It's a weak base. So that means you need to use the POH version of the Henderson-Hasselbalch here. Pay attention to that. Whatever one is the weak. If your weak is an acid, use the pH version. If the weak is a base, use the POH version. But notice here, they gave us the pH in the problem. So you would have to do 14 minus the pH to get the POH, and the POH is 5. All right. Also, you're going to need to get the pKb here in order to do the problem. So they gave us the Kb. We know that the negative log of Kb would be equal to the pKb. So when you do the negative log of the Kb, you get 4.74. Now we're ready to take this information, plug it into our Henderson-Hasselbalch, and go from there. So again, we're going to be using the POH version of the Henderson-Hasselbalch equation because we have the weak base. We plug in the POH that we just found along with the pKb here. Realize in this problem, they're asking us for the number of moles of NH4Cl. That's part of the conjugate here. We already know the concentration of the weak base, but in order to figure out the moles of the NH4Cl, which is the conjugate, we're going to need to solve for the concentration of the conjugate here, or the concentration of the acid on top in this equation. So you have to pay attention to this. We're not solving for the POH this time using the Henderson-Hasselbalch equation. We know that. We're going to solve for the concentration of the conjugate acid in this case, and then we're going to have to use that information to get to the moles here. So again, this does require some thinking. You need to pay attention to what you're actually solving for. But this is the weak base, so we're able to plug that in here on the bottom. So now we just need to do the math here in order to solve for the concentration of the conjugate acid. I just want to show you the steps here. So the first thing I did was I subtracted the 4.74 by both sides, and now I have 0.26 equal to the log of the concentration of the acid, which is what I'm solving for, all over the 0.10. Now I have to essentially get rid of the log here. To get rid of the log, I have to do 10 to the power of 0.26, right? So make sure you understand the math here. To get rid of the log on the right, I do 10 to the power of the number here on the left. So 10 to the power of 0.26, I'll have to get a number, and then I can continue the problem here. When I do the math, 10 to the power of 0.26 gives me 1.82. So now you just need to cross multiply, and then you get the concentration of the acid here. This is not the end of the problem, though. This gives us the concentration of the acid being 0.18 molar. We want to know the number of moles of the NH4Cl. This is the concentration of the conjugate. All right, we need to get now to moles using this. pretty simple calculation. We know we have 2 liters here. We know the concentration is 0.18 moles per liter. Liters would cancel. Now you'd be in moles here of your conjugate salt. So you were able to use this to determine the number of moles. So this is just showing you a different version of the buffer problem where you're not solving for the pH or the pOH, we're actually solving for one of the substances here, either the concentration of the acid or the base conjugate here using the equation. And then we were able to take that then to moles. So you have to pay attention to what you're solving for, but you now have seen another version here, another variation of one of these buffer problems. Let's look at another buffer problem here. This one says a buffer is made by adding 0.30 moles of acetic acid, Ka is given, and 0.30 moles of sodium acetate to enough water to make 1 liter solution. Again, we know this is a buffer because we have a weak acid along with its conjugate. It says the pH of the buffer is 4.74. We want to calculate the pH of the solution after a certain amount of NaOH is added. So we're not finding the pH of the buffer here. We know the pH of the buffer. We're trying to figure out the pH after we add a certain amount of NaOH. Okay, so we have to think about this a little bit differently here. We are adding base. All right, so in your head, you should be saying, okay, if I'm adding base to a buffer, the base is going to get attacked by the acid part of the buffer. Okay, so according to the problem here, we have 0.30 moles of the weak acid. Right? If this was in concentration, we would have to figure out how many moles of this we have, but it's nice, it's in moles already. So what this means is, if I have that many moles of acid in my buffer and I add this many moles of base, okay, the added base and the acid that's there are going to attack each other, and essentially the acid is going to annihilate the base and it's going to destroy it. All right, but in the process here, some of that acid gets used up as it's reacting with and destroying the base. So you take the moles of acid that were in your buffer, subtract away the moles of base that are kind of being destroyed here, if you will, and you have that many moles of acid left over. But you need to think about this though. In the process, all right, you had a certain amount here of the conjugate. When this acid is reacting with the added base, it's going to form more of the conjugate. You need to go back and look at those previous slides when we saw that when the acid part of a buffer is going to react with base, you're going to use that up. It's going to decrease, but then you're going to form more of the conjugate that's in the buffer. So you have to take the amount of base that you're adding here and add it to the conjugate. All right. So this is how many moles of conjugate you had in your buffer. The amount of base you added, you're going to add to it because you're forming that much more of the conjugate. So now you have your new amount of moles of the conjugate. This really needs you to think a little bit here, and you need to pay attention to what is actually happening in a buffer. And that's why understanding those previous slides about which part of the buffer is going up and down when you're adding acid or base is important here. So if you have a buffer and you're adding base, the acid part of the buffer is going to go down because it's reacting with the base. The conjugate part of the buffer is going to go up. And then the opposite is true. If you'd be adding acid to this buffer, okay, the base part of the buffer would go down as it reacts with it, and the conjugate acid part of the buffer would go up. So now I have my new moles here of the weak acid and the conjugate. Now I can take these and get them into Henderson-Hasselbalch once I pay attention to their concentration. On the previous slide, we determined the number of moles of the weak acid still remaining and the number of moles of the conjugate that are here as well. But in order to use Henderson-Hasselbalch, we need their concentration. So just be aware of that. Don't just plug these numbers in. You must be in molarity. In this case, it's actually pretty easy because we only have 1 liter here. So the moles basically become the concentration when you divide. So you have the concentration now of the weak acid and the concentration of the conjugate here that are going to be present after you add this certain amount of NaOH. Now that we have the concentrations, we can plug this in here to the Henderson-Hasselbalch equation. Since the weak part of my buffer was the weak acid, I need to use the pH version of the Henderson-Hasselbalch equation. You can quickly here find the pKa, all right, do the negative log of your Ka, get your pKa, comes out to be 4.74. And then when we have our concentration of our acid and base that we just found, we plug them into the equation here. And when you do the math, you find out that the pH is 4.80. All right, so it's pretty close to the original pH. It did go up a little bit because we added base to this, but the base got destroyed, and we pretty much don't see a major jump in pH here because that's the point of a buffer. All right, it's going to resist these changes in pH. So this is another version of the buffer problem where you need to think about what an amount of acid or base added to a buffer will do to the amounts here of the weak and its conjugate. So definitely know how to do a problem like this. I just want to mention real quick here that, buffers are actually very important here in our everyday lives. We need buffers in our body to maintain pH levels in order for certain enzymes here to work correctly. Human blood has to have a pH between 7.35 and 7.45 in order to function normally here. So there has to be buffers in the blood to prevent these major swings here in pH. If the pH falls below this, that's acidosis and eventually could lead to death. If the pH rises above that point, that's called alkalosis, and eventually it could lead to death. So we need these buffers in our blood in order to attack any, acid or base that might mess with the pH, and we need to keep this stable pH, right? And buffers help with this. So buffers are definitely very important here. Let's look at an example here. This says a chemist needs a solution buffered at 4.30 and can choose from the following acids and their salts, which should be chosen. So we're given 4 acids and their Ka values. So we want to know which of these we should use. All right, let me give you a hint here. All right, find the pKa values of each of these acids. If you remember, we know that when you have a pH equal to the pKa, you're going to have here an ideal buffer. You're going to have the most effective buffer. So they told us in the problem the pH was 4.30 here of this solution. So if you do the pKa of all these acids, the one that's closest to 4.30 is going to be the one that you want to use here. So you can do all the pKa's on your own, all right? But the one that comes out to be the closest here to the 4.30, the pH that we are buffering this solution at, would be the benzoic, all right? So anytime you're asked here if which acid should be used, just do the pKa of their Ka, and when you have the pH closest to that pKa, you'll know which one should be used. Let's look at an example here. This says, what is the pH of a buffer solution that is composed of 0.45 molar NH4Cl and 0.15 molar NH3, and we're given a Kb. I hope you realize here the Kb kind of gives it away, but our weak is going to be the NH3, the weak base. Because we have this Kb, a weak base, we need to use the POH version of the Henderson-Hasselbalch equation. So it's going to be POH is equal to the pKb plus the log of the concentration of the conjugate acid all over the concentration of your weak base here. Before I can go any further, I need to find the pKb. So I know pKb is going to be equal to the negative log of Kb, and that's going to be equal to the negative log of the 1.8 times 10 to the minus fifth that was given in the problem. When I do the math here, comes out to be 4.74. So now I know my pKb, I know my concentrations of both the conjugate acid and the weak base, so I can plug in here. So I have POH equal to the 4.74 plus the log of the 0.45 on top, because that's the concentration of the conjugate acid here, divided by the concentration of the weak base, which is 0.15. So when I plug and chug this, you should get 5.22. Before you get all excited and circle this and think this is your pH, remember this was a POH. So we have to do pH plus POH equals 14. 14 minus the 5.22 is going to give me 8.78 here. And this makes more sense for the pH. Again, we were dealing with a weak base. We would expect this pH to kind of maybe be more in the basic region. So this was just another version of a Henderson-Hasselbalch equation with a buffer, paying attention to the fact that we had a weak base. So we need to use the POH version and then convert back to pH at the end. One more example here. We want to calculate the concentration of sodium benzoate that must be present in 0.20 molar HC7H5O2 to produce a pH of 4.0, and we're given the Ka here. All right, so what I want you to do here is I want you to try this problem on your own. Pause the video, make sure you can do it. It's important that you can work through these problems on your own. And then when you rejoin, I'll have it completely solved for you and we'll see how you did. So pause the video right now and try this. Hopefully this is the answer you got here. We're looking for the concentration of the conjugate. We already know the concentration of the weak acid here. They gave us the pH, so we're using the pH version of the Henderson-Hasselbalch equation because I have a weak acid. You realize here, hopefully pretty quickly, that you need the pKa. So when you plug into your equation, you know the pH already. You've just found the pKa. You're going to have the log of the concentration of the conjugate base, which is what we are looking for. That's what we're looking for here, all over the concentration of your weak acid. So I did the math here for you. All right, subtract the 4.19 from both sides first. In order to get rid of the log, you do 10 to the power of the negative 0.19 here. When you do that, you get 0.64 equal to the concentration of your conjugate base all over 0.2. Cross multiply, and then you get the concentration here of the conjugate base being 0.13 molar. All right, so you definitely need to understand what's going on with buffers. You need to understand what happens when you add acid or base to the buffers, how they can resist changes here, and then be able to do different problems with buffers.